Hello everyone, this video will go over how SailGP gets results from the AD service. What is SailGP? SailGP is a global championship where 9 Sail Grand Prix take place across the world. The boats hit nearly 100 kilometers per hour where they compete for the podium and $1 million. There are around 125 sensors per boat, 9 boats, and they generate a billion data points every single day. It is impossible for a single or even multiple humans to scan through this data as a day-to-day operation. SailGP uses our cutting-edge anomaly detection service to find failed sensors and other issues on the boats. Using this, they have detected a failed pressure sensor that could have been a catastrophic failure. They also start to see anomalies way before anything fails, and it provides a head start on situations like avoiding any breakdowns, estimating the life of their parts, and for scheduling any servicing and other various diagnoses as well. Now, I will demonstrate how SailGP did this and how you can do the same. I will briefly walk through the steps taken to identify sensor failures in the SailGP data. First, we train a model using an earlier race data. This has been looked into by SailGP and contains no anomalies. We create multiple models for multiple sensors. Some sensors have high frequency data, and this is done to optimize accuracy and minimize runtime for fast results. After the model is trained successfully, we can use them to detect failures. This involves ingesting the latest race data from the database as soon as it is streamed from the boats to Oracle. To provide swift results, we use a jobs pipeline to schedule and parallelize them. We finally save, post-process, and plot the results. This notebook will go over creating a model with clean data that is reused for detecting anomalies in every race. We will use this notebook to pull data from the database, to perform pre-processing, and upload that to an object store, what can then be queried by a model for training. First, we import the required libraries for the project here. To pull the data into the notebook for pre-processing, we store the name of the boat and the 58 sensors that we want to query the data for. We also assign to variables the source of the data and the time period of the data we want to feed for training. Consider these filters or conditions. Once this is done, we query this cell by creating a query to pull the data from the Oracle DB that satisfies the conditions assigned in the previous cells. Later, we run this cell to download all the raw data into the working directory if it does not already exist. The next step is the pre-processing. This involves cleaning up the timestamps and extracting the required columns from the raw data. Optionally, we could also choose a different sampling frequency for purposes like faster training and handling high frequency sensors. Once this is done, we upload this pre-processed data into an object store, which is ideal to be consumed by the model. To upload an object in the object store, we use the command oad.uploadObject followed by the file name. Once uploaded, to list all the files in the object storage, we use the command oad.objectstorage.listObjects. We pass the parameters namespace and buckets, which we set up with the OAD connection earlier. To create a model, we first need to create a project to organize the models. We now create a data asset to connect our pre-processed data from the object store so that we can train the models. First, we can check the existing data assets using the command oad.listassets and pass the project ID as the parameter. We can then use the command oad.createDataAssetOS to add new files from the object store into the project's data assets. Now, to create a model using the existing data assets, we first get a list of active models using the command oad.adclient.listModels. We then create new models using oad.createMultipleModels from data assets for the data assets that have not been created yet. Now we can use the following code to report on the state of the models and check whether the model is still being created or is active for the inference workflow. We will now move to the inference workflow. Once the model is active, we will use this inference notebook to detect anomalies using the created model. This notebook goes over preparing the testing data, followed by inferencing with the model trained earlier. We first import the required libraries for the project here. We then create directories to store the outputs and the logs. We have a few helper functions to help with the inferencing, post-processing, and saving the results. Here we create variables to store the details of the sensors we want, the source of the data, and the time duration of the data we want to detect the anomalies for. We can also choose the boards we want to get the results and the data for. Here we create files to store the jobs and their status logs. In this cell for the detection job, we first start by ensuring the directories exist and create any that do not. We then go over some conditions that require dropping certain sensors that are not active. Here we use an SQL query to download data into the working directory using the filters for time interval, boat, and model ID parameters that we saved earlier. Once we have all the data required, we can proceed to perform an inference call on this data using the model created earlier to detect anomalies. To inference, we first set up a connection to the OCI AD service. For each test file, we create a new job using the schedule jobs command. This preprocesses the test data and runs it through the trained model to generate anomaly results. Once we have the raw results, here we have inbuilt functions to perform consolidation to remove any minuscule variations and to save the results into the directories we created. We also extract summaries for all boats and sensors for further study of results. Here, the outputs of the logs show the following information: the created jobs, their status, any missing values, and the location of the saved results. We now conclude the two notebooks. Here are some results captured using this system. This is the sensor read from one of the sensors monitoring the hydraulic pressure tank accumulator. In the chart above, you are seeing 7 million data points per sensor ingested each day, give or take a million or so. As you can see, the sensor started going RE around 11 a.m. the previous day. The anomalies continued, and eventually the sensor was replaced at the end of the day with a new one. As you can tell, things move rapidly in this system. Finding an anomaly by just human observation is almost impossible. In order to not flag every small variation as an anomaly and throw up a lot of false positives, the system was designed with a consolidation logic that analyzes a rolling window of detected AI anomalies and only flags it for human intervention if a threshold is exceeded. This is the Team USA boat. The top picture shows raw anomalies marked on the graph with the green overlay on top of the blue signal line. The bottom picture shows the same signal but with the consolidation logic applied. As you can tell, there were no anomalies that were flagged for a human to take a look at. Now let's take a look at another team's boat. This is the exact same sensor but on the French team boat. You can see the graph with the anomaly output from the anomaly detection service has just lit up the entire chart. Even with the consolidation logic on the bottom chart, it is very obvious that there is something very wrong with this sensor. Sure enough, there was, and it was replaced. The Australian boat was in sail mode but had put an emergency stop in this issue. This can be due to an emergency or when the boat is taking a break. Using multivariate anomaly detection with no prior knowledge, we were able to figure out before the trials when an emergency stop was executed during the sailing, which would have otherwise been missed. You do not have to tell us all the conditions where an issue may occur. We are able to flag the event that we have not seen before. Sometimes we see multiple boats and sensors are being flagged with high anomalies due to unforeseen external stochastic events or due to hidden variables. We also look at the comparative flag rate to find out which boat is actually failing. Here we see that for one particular sensor, all boats have an anomaly flag rate of around 10%. This is unnaturally high for a singular boat. With this focused comparative analysis, we are able to figure out that it is an external factor and dive deeper to pinpoint causes of specific anomalies. With this, I would like to conclude the demonstration.